Hello everyone, I'm Dan and this is the video portion of my final project for the class Advanced Metallic Materials and Processing, Forming and Deformation. I'll be covering the U.S. patent history of electromagnetic forming. Electromagnetic forming, which is a kind of high strain rate impulse forming, has an extensive patent history starting in 1961. It has such an extensive history that it would be impossible to even briefly cover each patent individually in a 10-minute video, so I've had to be selective with what to include. I'll be focusing on English language US patents in Class B21D26 and its child classes, that is, shaping without cutting otherwise than using rigid devices or tools or yieldable or resilient pads, that is, shaping without cutting by applying fluid pressure or magnetic forces. There have been 290 total English language US patents in B21D26 and its child classes granted between 1961 and the present dealing with electromagnetic forming, and we can see that a lot of work on this topic happened in the second half of the 60s through the mid-70s, followed by a dramatic drop in related patents until a modest revival in the 2000s. Another trend that is less immediately evident in this graph, but which will become evident through examples shown in subsequent slides, is a transition from patents describing fundamentally new and innovative ways to use EM forming in its early history to increasingly specific and niche industrial applications of EM forming in recent years. The critical first patent describing EM impulse forming was a patent by Harvey Brauer in 1961. This patent described many of the fundamental operations possible through EM forming, including joining, compression, and expansion of hollow tubes by solenoidal coils, and forming conductive sheet metal against a die using a flat coil. Electromagnetic impulse forming can be thought of as an RLC circuit, where energy is stored in a capacitor bank, released in a pulse to create a strong current in a coil, creating a strong time-varying magnetic field near the coil, inducing current flow in a conductive workpiece in the opposite direction due to Faraday's law of induction, and creating a repulsive force between the workpiece and the coil because the current in these conductors is flowing in opposite directions. Only 1 year after the first patent on EM forming was granted, Gulf General Atomics sold the first commercially available EM forming machine. A number of critical improvements to the basic ideas originally proposed by Harvey and Brauer were described before 1965, including use of sequential EM forming steps, simultaneously using induced currents to heat the workpiece, use of a capacitor bank to store charge, use of flux concentrators to more precisely apply forces on the workpiece, and EM forming by pulling rather than pushing forces. This is also the period where the processes of electromagnetic shearing, threading, and forming of closed vessels was first described in patent literature, as well as the period where explosive forming by vaporizing a conductor to form a workpiece was first described in patent literature. The way described to create an attractive force between the inductive coil and the workpiece is to slowly increase the magnetic field until the field is suitably strong and the workpiece is saturated, at which point a fuse is triggered, stopping the current flow through the coil, collapsing the magnetic field, and causing eddy currents in the work, that is, the workpiece. Simultaneously, a current flow is induced in a secondary coil in the same direction as the eddy currents in the workpiece, causing an attractive force between the two conductors. In the late 1960s, EM forming trended toward automation, and several additional important advancements extending the applicability of EM forming were described. EM forming was used to automate the flanging and separation of metallic cans, and, by the end of the decade, the capping of glass bottles. In 1966, a patent was granted for an EM device using a sacrificial metal conductive driving plate to press a non-metallic, non-conductive workpiece against a die, revealing the ability of EM forming to form non-metal products. In 1968, NASA put a spin on this idea and described a method to use this metallic driver as a hammer for forming. During this time, academic literature demonstrated that EM forming could join dissimilar metals and even dissimilar materials, such as in the example of a metal cap and glass bottle, and models were developed to describe specific cases of EM forming, such as what the required field strength would be to compress a homogeneous isotropic rotationally symmetric tube using the Tresca yield criterion. A significant amount of related literature and patents were published in the Soviet Union during this period as well, including the first mention in patent records of magnetic impulse powder consolidation in 1969. In the 1970s, U.S. patents were granted for EM impulse welding the overlapping surfaces of telescoping pipes with inwardly or outwardly flanged ends, the composition of a metal elastomer composite driver which could be used to form non-conductive workpieces without destroying the driver, as well as methods to reduce the region of a workpiece that would be exposed to an induced heating current within an apparatus that used EM forming to perform a wide variety of metalworking processes. This decade also saw the development of a method to measure the velocity of a high-speed reflective surface, such as the surface of an EM-forming workpiece, a German patent for high-current large cross-section coils, literature on the microstructure of impulse-welded metals, and a comprehensive Russian-language electromagnetic metal-forming handbook released in the USSR. Though academic literature on EM forming continued being published throughout the 80s, the number of U.S. patents related to this topic granted took a sharp decrease. However, this decade still saw, among other published patents, a portable device to generate attractive forces by EM forming, a method to join a metallic sleeve to a ceramic shaft without breaking the ceramic shaft by initially compressing the shaft mechanically, an EM forming method of shaping wheels from blanks, an apparatus which uses a single pair of conductive rails, here and here, which form a single-turn conductive coil around a workpiece when the die is closed around the workpiece, and a flexible, reusable driver composed of many layers of conductive foil for the shaping of non-conductive workpieces. By 1988, the U.S. Navy also patented a device to simultaneously form a disc into an armor-piercing projectile and launch said projectile using EM forming, which is notable since it was the first weaponized application of EM forming I found in patent literature. By the end of the decade, the first experimentally verified FEM of EM forming was also published in academic literature. The annual number of U.S. patents related to EM forming remained rather small until the late 1990s. During the 80s and 90s, academic literature was developed by multiple authors describing the effects of high-speed forming on ductility and formability. The particular example I have shown here is from Dr. Dane's 1992 paper on the effects of strain rate on forming limits of interstitial free iron. Notable U.S. patents in this decade included a new way to join pipes by a bridging sleeve compressed into ridges cut into the ends of tubes, methods to corrugate metal pipes, a method to dramatically expand tubular workpieces by simultaneous axial compression and electromagnetic radial expansion, and novel designs for work coils to more precisely control the magnetic field by splitting or reversing the direction of current in the work coil, attributed to Dr. Dane and others at OSU. In 2002, the first biannual International Conference on High-Speed Forming was held in Dortmund, Germany, and a lot of literature from this conference was published the following year. This has become a significant biannual event for the field. The first 3D FEM simulation of electromagnetic impulse forming was presented at the second International Conference on High-Speed Forming, and the International Impulse Forming Group was formed at the third. In this decade, there were also many patents filed for the use of EM forming in the automotive industry, including joining of vehicle frame components, methods to finish hydroformed motor vehicle members, simultaneous joining of multiple underbody structural members, and others. Any patents granted from 2005 or onward are also still active, since U.S. patents generally last 20 years. In 2011, an extensive review was published on EM forming by Fisk and others, which was very helpful in presenting an overview of academic literature. Patents granted during this decade included a method to reform the shaped ends of tubes from a shaped state into a state more closely resembling that of a fresh, simple extrusion through several sequential steps of EM tube expansion. Methods for forming metallic glass workpieces, integration of EM forming into other metal forming systems including roll mills, advancements in use of magnetic impulse forming to consolidate metallic powders, and a great deal of literature on EM forming done and published in China. Patents continue to be granted for new methods and apparatuses utilizing EM forming in the last 5 years, particularly for automating the forming of metal containers. The 2022 patent Systems and Methods for Electromagnetic Forming of Containers is excellent in describing how many different processes including expansion, necking, flanging, and embossing can be accomplished in series using electromagnetic impulse forming. The most recent patent in this class is relatively simple, describing the forming of metallic pouches by EM expansion in late 2024. So far, there have been no patents in Class B21D26 related to electromagnetic forming granted this year. Thank you all for listening. I will quickly show my references, and am happy to provide anyone who has questions about a particular patent or other resource with a link.